knowing's well. Little second to naughty, prevalent power. Your arms are calling out. They wave like a swarm of sound. You pull the sound from scores of notes. You step the stage and take control. Connected as in a moment of silence. Your body erects a pulse of wind. Fun, carry on, hectic, man, you invite. Your arms are calling out. They wave like a swarm of sound. You pull the sound from scores of notes. You step the stage and take control. Those arms are calling out. They wave like a swarm of sound. You pull the sound from scores of notes. You step the stage and take control. Control, 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 control.
All right, so picking up where we left off, we were looking at trees and tree-based data structures, and we had introduced this notion of binary search trees, where everything has a key, and everything in the left subtree is less than that key, everything in the right subtree is greater than that key, so that all of our operations are going to be efficient, assuming that you've got a depth that is order log n. Of course, that's not a guarantee. So let's review what we did as far as the development of operations. Searching, you start at the root and traverse, and compare, I should say, compare to the current node, right? Traversing left, right, or stopping, depending on the result, right? So we check, for example, let's go over here to our example. If we get lucky, of course, we start at the root and we're searching for 50, then we're done, right? If we ever get lucky and we find that what we're looking for, say, 45, then we're done, right? But if we ever get unlucky and we've fallen off the edge of this tree, then we stop and say that it was an unsuccessful search. And the way that this works, again, is we start at the root, and if the thing that we're searching for, say 45, is less, then we traverse left. If the thing that we're searching for, 80, is greater, then we search right, right? And we go left, right, as many times as we need until we get down to the bottom here, say 13, we end up not finding it. We then looked at how to insert things, right? You insert elements always as a new leaf, right? Inserting where the element should be if it were already there. So, for example, inserting 13 simply means that we're going to find where it should belong. It should belong right here as the right child of 12, and that's where we end up inserting it. 13 as a new right child. And we took you through the code to do this. Right? So, for example, we also did in-order traversals, realizing that that would actually print out the binary search tree in order. Where's the insert? Yep, here's the insert. First of all, we also have a corner case here, where if it's an initially empty tree, then we create this new binary tree node, which is the root. We increment the size, and we're done. So in order to insert something, we need to keep track of the previous one, because once we've fallen off the tree and the current is now null, we still need the previous one in order to set its left or right child. Right? If we ever find the thing that we're trying to insert, then of course it's a no operation, and we return false in this case. It did not have an effect on the tree. Otherwise, the thing that we're trying to insert is less than the current node, and so we traverse left. Keeping track of both the previous and the current here. Otherwise, we traverse right, keeping track of both the previous. Now, one thing that I did not do last time that I've added since then is this one right here. At the end, after we've broken out of this loop, we need to create a new leaf node here, but I was not setting its parent. So potentially, we'll want to, from a node, we may want to traverse back up the tree as well. And it's only possible if we're keeping track of the parent along with everything else. We've got, then one last comparison is made to determine whether or not we should insert it as a left child or insert it as a right child. In either case, we increment the size and return true to indicate that it was successfully inserted. Contains, we started out with that one, which is basically the same algorithm. Now what I want to do is I want to look at the other part of CRUD, right? Create, retrieve, update, and destroy. Update, we're going to ignore that one because updating is simply just finding the element, changing its value, or removing it and then creating a new value. So you can do that in the terms of the other three. What I want to look at is the destroy here. How do we delete something, right? So delete. So I'm going to go through several examples here. For example, what if we wanted to delete, say, 75? Right? What's the first thing we need to do? Well, we need to determine whether or not it's in the tree, right? We can't delete it unless we find it. So we end up doing a search algorithm. We come down here, we find that 75 is right there. Right? Now, if we were trying to delete 76, then we would come down here again and find that it doesn't exist, and that would be a no operation, or we could throw an exception, or return false, or something like that. But otherwise, if it's deleting 75 here, well, the first step is, step 1, find it. Right, find the node containing the element that you want to delete. Once we've found it, we need to delete it. So, how can we delete 75? If no children, how could I end up severing this connection here?
Remove the left child of the baby.
Right. So set parents left or right reference to null. Okay? Or nothing. And that ends up deleting the entire node. And now it's gone. Okay? Let's back this up and let's try to delete something else. What if we were to delete, say, 15? Same as before, we need to find it. So I come down over here, come down over here, come down over here, come down over here. Oh, there it is. I need to delete it. Can I merely delete its parent's reference? Oops, sorry. I want to delete 15. No, what happens? We lost 12. In fact, a whole bunch of stuff could have been hanging off of this node, and we lost everything. So back that up. Ideas. alternatives here. What I want you to do is I want you to focus on these 3 nodes right here. Now, if I were to remove the entire tree, everything else in this tree, I've got this node A, B, and C. I want to delete the middle one. What does that look like to you? A linked list. Do we know how to delete from a linked list?
Yeah.
Yeah. How?
Make the child of 10, 12.
Exactly. Just simply circumvent this over here, and that leads to this being severed completely. And then what you do is you let it dangle again, and now it corrects itself and it looks more like a tree. So, my second case here, if one child, right, treat as a linked list. And we know how to do that. Okay? Great. So, give myself some more room here. Let's think about how we could delete something else that's a little bit more problematic. What about deleting, say, 50? Right? Here's 50 right at the root. First of all, find it. Done. It's right there. Okay. Well, in this particular case, what could I do? I could say, all right, well, what I'll do is I'll delete 50 here, right? And I will make 60 my new root node, and this left child ends up being over here. Right? And then let gravity take its course. Right? That'll work. But would that work in general? No, why? Because I could have something hanging off of this, right? I could have an entire tree over here. Oh, actually, let's just make it one node. What could be here right now?
7.
Could I put 70 there, you said?
No.
Nope. 70 is less than 60.
Yeah, so sorry. Let's go with 55.
Okay, 55. I buy that. Why? It has to be greater than 50, but less than 60. So there's your range right there. 55 is right in the center. Right? Now, can I do the same thing that I did before and make 60 my new root node? That would look like 60, and then 40, 55, and then 90 is still hanging off of that. Does that look like a binary tree to you?
No.
That looks like a ternary tree to me. Right? So that's not going to work. What I want you to do is focus on this left subtree over here. There we go. Think about what you could take from this left subtree to promote it up to this node up here. All right, we're going to delete 50. We've taken 50 and we've thrown it out. Okay? This has left a gap. Right? I don't want to change the topology of the tree too much, right? Because if I've got 3 children, okay, now I have to go down the tree again to find somebody else, et cetera, et cetera. I'm going to go ahead and find something in this left subtree that I could replace 50 with, and it still would be a binary search tree. So think about the binary search tree properties. What could go here? It has to be something that is greater than all of these. Right? Greater than or equal to. So,
So grab 49.
49. All right. Why 49?
It's as close to 50 as you can get, and it still is greater than 40 less than 60.
What about 49 relative to everything over here?
It's bigger than all of that.
So in other words, it's we have a name for that, the maximum. Right? Okay. Alternatively, what could we have done with respect to the right subtree? I need to promote something up here that is less than everything over here. We call that thing the minimum. Right? We won't worry about that though. Okay? We've made our choice and we're going to go to the left subtree and find the maximum. First of all, how do I do that? Let's think about this more generically. Right? This is the key that I'm about to delete. All right? This is its left child right here. Right? And then there's this big giant tree maybe hanging off of it. Okay? How do I find the maximum in the left subtree right here?
Correct the right terms.
Yep, just keep going right. Why?
If the bigger child's over the right.
It's always going to be to the right. Okay. So all I have to do is go here and don't even look at things. Just keep going right until there is no right child. And you found the maximum. Okay? Well, that might lead to a problem though. All right, so suppose that I've got, why is that not erasing? There we go. Whiteboard problems even on an electronic whiteboard. All right, so I've got my maximum right here that I want to eventually promote up to whatever I just deleted, okay? That means that I'm gonna have to take it out and replace it with something. Well, if there are no children, we know how to deal with that because that's what we started out with. If there's one child, we know how to deal with that because that's the second thing that we looked at, right? But what if there are two children here? Okay? I'm back at square one, right? But now think about this. Is this possible? What was the, let me call this L and R. Right? And I suppose that this was the maximum among all of them. But binary search tree property, tell me about R versus the max.
It's greater than the
Right.
max.
Exactly. So was that the max? No. Right. So you will not have a problem. It's one of the first two cases. All right. What do you mean? What do you mean? It could have 0 children, 1 child, or 2 children. But 2 children is not possible. So it's either 0 children, in which case it's a leaf, you delete a leaf, or there's only 1 child, the other child, right? The left child, in which case we know how to deal with that. All right, let's come back over here. Now before we go any further here, I did want to show you that I've got yet another way to test this stuff. So for example, let me go ahead and show you a visualization that I've got right here. Let's go ahead and create a new binary search tree. There we go. And remember what we were doing last time? I think we created a random R is equal to new random. And then for int I equals 0, I is less than n, or 10, say, I plus plus. And then what we'll do is we'll randomly insert these elements. T dot insert R dot next int. And we'll keep it small, at most 99, 0 to 99 values, okay? Now, we did a few things. For example, we did some testing here. We saved all those off into a list, and then we asked, did it get in there properly? But all we got out of that was true, right? We didn't know whether or not the topology was correct. So we thought, okay, well, if we did an in-order traversal on this, then we would get the topology in that it should be in order, right? That's still not enough for me, because for me, seeing is believing. So what I wanted to do is I wanted to actually visualize this. So system.out.println, if I just do this, right, print out T here, what's wrong? Oh, I know. I need to create a new treeutils.cmp integer. All right, there we go. This is just a comparator here that orders things in ascending order. Okay. There we go. Let's go ahead and run this. All right. If I just print this out, of course, I'm going to go ahead and get this memory address. I could print this out in as an in-order list. That would just give me numbers. It wouldn't give me the topology of the tree. So what I did instead is I went and created another algorithm, treeutils.toTixie. So if you've have you done LaTeX? You've done LaTeX in your lab reports,
We
right?
have.
All right. Have you learned any like to draw things? No. Okay. Oh,
Tables.
tables, sure. But like figures? No? Something that looks like, say that? No. All right, well, there's an excellent package called Tixie. And I don't know what it stands for, but it's German or Norwegian or something, I don't know. But in any case, let's go ahead and see what this looks like. There's the Tixie picture of this randomly generated tree. I'm going to go ahead and go over here to Overleaf. Have you been using Overleaf for it? Okay. So let's go ahead and switch to my editor over here and cut and paste this Tixie picture and recompile it. Hey, what does that look like to you?
What you made.
Yeah, well, it was random, right? All right, it looks kind of like what I made over here. And do you think that I actually drew that by hand? No. Do you think I actually coded that Tixie picture by hand? Absolutely not. What I did is I created code to do it for me. Right? And as you guessed, it's kind of recursive. There's a header here to begin the Tixie picture, and then there's the root node, and then I do the left child, the right child, recursively, which creates child nodes and then makes calls recursively to create children of children and children of children of children, etc. Right? And so I've got this nice little way of visualizing my data. Seeing is believing. Does that look like a binary search tree to you?
Yes.
It does to me too.
It's not balanced.
Not balanced at all, no, but because it was random. Okay, so now that I've got another way of testing this stuff, let's go ahead and start implementing the delete method. So public void delete, tx. So all we're going to do is searches for the given value and removes it if it exists, or in this tree, if it is in, if it removes it if it is in this tree. There we go. Okay. So what's my first step? Let's outline this. 1, let's find it. Find the node containing x. Right? 2, if it is a leaf, then delete it. Delete it by modifying its parent's reference. Right? 3, if it has one child, right? Then how am I going to delete that? Modify the parent's child reference to the node's child. Right? Circumventing it, right? Going around it just like a linked list. 4, if it has 2 children, right, then I need to A, find the maximum value in the left subtree, right, and then B, replace the value in the node with that value, with the max, right, and then C, delete the max. Right? So there's my outline. Find the node containing x. That sounds familiar though, right? Didn't we already do that? A contains method, right? But does that return the node where you found it? No. So what I'm going to do is I'm going to redesign this method so that it's more useful to me. Instead of returning true, it contains x, it will return a binary tree node containing x, if it exists. Okay? So I'm going to clean this up a little bit. There we go. There we go. So we start at the root, and while we're not there yet, we don't return true. If we find it, we return the current. All right? Otherwise, we go left or we go right. And if we don't find it, then what should we return? No. I like that. Now, I'm not going to call this contains because that's true or false. I'm going to call this get node containing x. Okay? Now before I go on, should this be a public method? I'm a tree, right? Should I be giving my nodes out to you? Should I be leaking information about how I store stuff? That sounds like a leaky abstraction. So let's make this into a private method so that you don't have access to this, but I do as my tree, right? How does that help us maybe redesign this? I don't need to implement this twice. All I need to do is have the node, say you, right, is equal to this dot get the node containing x, right? And if u is not equal to null, then we know that it contains it. Return true. Otherwise, if it is equal to null, then we return false. It does not contain u. Can I clean up this code a little bit? If this condition is true, then return true. Otherwise, if that condition is false, then return false. So just return that condition. There. Yep, exactly. So don't have an if-else if it's not necessary. There we go. Much cleaner code too, right? And now I can reuse it. Right? So find the node containing x. Well, that's going to be a binary tree node t, and I'll call it u maybe. I don't know. There we go. Now, what happens when we try to delete something that doesn't exist? Try to delete, say, 76. Become okay. Well, it's null. So what should we do?
Well, say we did it.
Yeah, okay,
It's
so
not there.
if u is equal to null, then you're done, just return. How could we be a little bit nicer about it, though? How could we be a little bit nastier about it, though? We could throw an exception, right? How could we be a little bit nicer? Communicate that I tried to, but I couldn't,
Change void, yeah.
to Boolean and return false. I had no effect on this. Now document that before we forget, right? Returns true, code, true, if the delete operation had an effect on this tree, code, false, 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 otherwise. There we go. I like that. Right? So down here we'll end up returning true regardless of whether or not, you know, we're correct down here. I like that. How do I tell if something is a leaf? I'd really like to ask that. Who should be answering that question? Are you a leaf? Who do you imagine me talking to right now? No, well, the tree is not a leaf, but a node in the tree would be the leaf. If are you a leaf? Is leaf? Then I know what I'm doing here should be deleting the leaf. Ah, okay. It's not answering that question. Make it answer that question.
Child?
All right.
Has child?
Public Boolean is leaf. How do we know that we're a leaf?
We don't have the left or right child.
If this dot has left child is null, and this dot right child is null, then return true. Or same trick as before,
So, yeah,
just return the expression. Right. Now I know that they're a leaf. Okay. Let's come back over here. Get rid of this. All right, so how do I delete it? By modifying its parent's reference. U dot parent. Okay, I can get their parent because I've already designed the node to be able to do that. Okay.
and then delete the left or the right, whichever child it is.
Yeah. Who? So, have you heard of this? It's kind of a poem, but it's kind of a brain teaser, I guess. Right. So there's this guy, and he walks up to this portrait of this other person. Right? And he says, I know this person. Right? So, Joe over here. Right? He says, brothers and sisters, I have none, but this man's father is my father's son. Who's in the picture? Brothers and sisters, I have none. So here's Joe here. No brothers, no sisters. He's an only child. But this man's father, so whoever their father was, is Joe's, my father's son.
Is it Joe?
It's Joe. Right? It's a painting of himself. I know this man. right? It's me. Right? So get it? All right. So how do I know that I'm a left child or a right child of my parent? I need to ask my parents. Right? So, brothers and sisters, I have none, because I'm a leaf. But this man's father, who, my parent, is my father's son. Am I a left child or a right child? Right? If u dot get parent dot get left child is equal to you, then you are a left child. Right? And so I set u dot get parent to null. Their left child to null. Now, do I need to ask that question again? I'm either a left child or a right child. So u dot get parent dot set right child to null. Right? It's one or the other. There's no third child. Right? Okay. That looks pretty cool. Let's come over here, and I don't want to be random anymore. Right? Let's go ahead and insert some things. T dot insert 50. Right? In fact, I could go ahead and do this tree over here. Right? I could go 50, and then I could insert 40, and then I can insert 60, dot, dot, dot. Or I could have done that before class, and I did. And there it is. If you insert them in this order, you will get, not this one, but this tree right here. Okay? So I'm going to go ahead and grab that, what's called the large BST here, right? And tree utils. There we go. And just to show you that this is actually working, let me go ahead and grab that Tixie picture, come over here to the editor, and recompile it, and show you that it is indeed that same tree. Now, I've only implemented the deletion of a leaf node. So 2, 12, 75, 85, we could delete those and test all of those things, right? So let's do that. T dot delete, what was it, 12, T dot delete, something on the other side, 75. There we go. And then I'll print it out, just to make sure that it worked. It ran. Remember, I deleted 12 and 75. So let's look at this over here and recompile it, and 12 and 75 should be gone. Hey, it works. Careful. That was a large binary search tree. What if we'd done something else? What if, for example, T dot, or T is equal to new binary search tree. Shouldn't have erased it. Tree utils. I'm just getting rid of the old one. And then T dot add, I don't know, 50. T dot remove, or delete 50. And then print it out. Not add, what is it, insert? Okay, there we go. Oh. It's one of them pesky corner cases again. Right. We cannot get the left child because the return value of get parent is null. And it's happening where?
At the root.
On line 20 here. So insertion worked, but then deletion didn't. Let's come back over here and think about that. If you only have one node, it's a seed, right? There's no children, so it's a leaf. The root ends up being the leaf. There's yet another corner case, okay? So, corner case, 1.5, right? Corner case, if you are deleting the root. Right? So if you dot, let me ask that question again. Are you the root? Is root. Right? Then what? In fact, let me move it over here because this really is only a corner case when it's a leaf. Right? So 2.5. 2.1 here. Let me move it up here. And then I'll do an else if there. So who should be answering that question? Are you the root or not? Once again, I want the node to be answering that question. How do you know that you are a root?
You have no parent.
Parent is null. There we go. Now, if you are the root and you are a leaf, then guess what? This dot root is equal to null. Right? It's that simple. That's what corner case there. Right? Let's come back over here and see if it works. Yep, silence is golden. I don't want to have to print it out because gross. It'd just be like an empty tree. But I took care of that corner case there. Okay. Let's go ahead and get rid of these. Come back over here and think about the next case. If it has one child, then I modify its parent's reference and the node's child. All right, if u dot is only child, right, doesn't have a left, doesn't have a right, except that when I go to modify my parent's child reference, I'm going to modify either the left or the right. So if the thing that I have, I'm going to say that if I have a right child, then I'm going to make my parent point to that right child. If I have a left child, then I'm going to make that parent point to the left child. Right? So maybe I split that out into two cases. Right? And by the way, we are needed to make an else if here. Right? If it only has one child, u dot has left or dot has left child. Then it has a left child. And what should I be doing? I should make u's parent's left child point to u's left child. Right? That's a to do. Else if u dot has right child, then I will make u's parent's right child point to u's right child. Okay, and the rest of this case 4 eventually. All right, those are great questions to ask a node, right? Except that it's not answering them. So once again, what do? Come over here and add them. Public Boolean has right child. Return this dot right child is equal to null. Careful. Is my logic correct there? If it's null, do I have a left child? Nope. So if it's not null, do I have a right child? Yep. Same thing for left. Left. There we go. Ooh, left. There we go. Great questions to ask, and now it makes for much cleaner code over here, right? Instead of me having to ask, is it equal, not equal to that thing? Right? I shove that off into the class that it belongs in, good encapsulation, and instead I can ask basic questions like, do you have a left child? Or do you have a right child? Right? It makes it much cleaner here. So how do I make u's parent's left child point to u's left child? U dot get parent dot set left child to u dot get left child. Just as I would say in plain old English here. Now, u dot get parent dot set right child to u dot get right child. And I know that the right child exists, otherwise this condition would have been false. I know at least one of these is going to execute if it has exactly one child. Right? Or it does it. Let's think about the logic here. What if it has two children?
Well,
It has a left child, so I would end up doing this. Is that correct?
no.
No. Let's test this in isolation though first. All right, let's come back over here to my visualization and let's find some left and right child here. For example, 24 and 49. I could delete those pretty easy. So 24, 29. T dot delete 24 and 29. and then I'll print it out and see if it works. All right, come over here. There is an issue that will not show up or will not manifest itself in the visualization, but we will take a look. 24 and 40, oh, wait, what was it?
49, you did 29.
Oh, did it work?
Well, it
Yeah, because there is no 29, so it worked.
Yeah.
Sorry, 49. There we go. I wanted both a left and a right to make sure that they both worked. So come back over here and recompile it. This should be the same over here. Oh, what did I do wrong?
Yeah, you made it 48. No,
Oh.
you didn't get rid of 49, but it got it.
All right. So 24 and 49. 24, 49.
There's two 48s now.
Yeah. Okay. So back to the drawing board. Well, first of all, I don't think that this is the issue, but there is another issue here, right? So, in fact, there's an issue above, if you want to get technical, with respect to garbage collection. But what I'm doing here is I am making, let's just take 24 here because it worked, right? We're making 20's right child point to 24's right child, okay? But what about this reference back to its parent? We're not taking care of that. So what do I need to do to take care of that? I need to make it point back to the parent, right? 24's parent. So let's come back over here. I'm making you have a left child, so I get the parent and I set the left child to be the left child of you, and then I say that u dot get left child dot set parent to u dot, yeah, your grandparent, so you and then get parent would be the grandparent of the left child. There we go. Same thing for right. Okay. That looks good. I'm pretty sure that this is what it was, right? Let's go ahead and I can print this out twice. 24 and 49. 24, 49. Okay. Let's run this. Now this is going to give me two diagrams over here. Before and after. There we go. All right, so 24 works when it is a right child. 45, I'm setting my parent's left child to the left child. So there's a left or right issue here. Was I not reading this correct? U dot get parent, you have a right child, U dot get parent, set the right child to the right child. I'm wondering if the setters are correct. They're auto-generated. Right child, set left child, left child, left child. Get
So
left child, get left child.
it maintains the fact that, what was it, 48 is a left child of 49, and 48 should become a right child because that's what 49 was, right?
So I'm deleting 49, right?
Right.
So I need to, oh, good point. Right, this is the bug. I'm getting my parent. I'm a right child. So my parent has a right child. So the thing I want to delete has a left child but not a right child. So that makes us right here. Let me actually just go ahead and set a breakpoint. Okay. Oh, we never got to that point. Weird. So that's why it's not working, because it never got to that point. So let's go ahead and set a breakpoint there and switch to this. Yep, let's go ahead and step into that function. Yeah, step over, step over, step over. Step into that function. All right, I'm going to step over that. And U is a binary tree node with element 49. We successfully got that. All right, good. Step over that. Is it a leaf? It has a left child and no, uh-oh. It's 48 and 45. Okay, so that tells me that we screwed up the topology of the tree on this delete right here. That I'm positive that if we had done 49 in isolation, it would have worked. So let's do that. Verify over here with these two. There we go. And recompile this. All right, we're just deleting. Nope, it's still screwed up. That's not right. Darn it. I'm not seeing it. All right, let's rerun that. And step into, step over, step over, step into, step over, step over. It's not going to be a leaf. But why does it have a left child and a right child? Oh, no, sorry, it's right child. I was looking at the parent, duh. Sorry. No, this is correct. Okay, so it's not a leaf. We're going to go over this correctly. Good. Now, do you have a left child or a right child? 49 has a left child. So we should step into this condition. Great. Now let's walk through this. U is 49. I get the parent of it, which is 45. Is that correct?
Yeah.
45. Okay, good. And then I set its left child to use left child. Use left child is 48. That looks good to me too. All right, so step over. And we just updated my parent's left child. Which is why we're getting this, right? My parents, it should not be a left child, right child. It should be relative whether or not I am a left child or a right child. U is, right? So let's stop this and come back over here. There we go.
You got it.
Left child, so not left child, X child, point to use left child. Because I have one child, right? I need to get my parents. So if U is a left child of parent, then set left child of parent. So if U dot is left child, I like that question, then I will set the left child. Else, U is the right child, so we will set U dot get parent dot set right child to U dot get left child. There we go. Is that correct?
It looks right.
That looks way better than to me too. Otherwise, I'm going to set my parent no matter what. Right? Okay. This looks like a great question to ask the binary tree node, right? So this is a great question. Boolean, public Boolean is left child. All right, I need to know if I'm a child or not, right? So if parent is not equal to null, right? I have a parent, so I am a child, otherwise I'm not a child at all, right? And parent dot get left child is equal to me. How do I say me in object-oriented programming? This. Right? Then I am a left child. Otherwise, return false. So, what should I do to clean this up? Just simply return that expression. By the way, I always do this. When I'm simply going to return an expression, I always write it out as an if-else statement, and then I simplify it, just so that I have the logic correct in my head. Right. We're probably going to want the same question for right child. So if my parent's not equal to null, and the right child is equal to this. There we go. Come back over here, and let's use that. I need to make sure that I'm doing it on the this one as well. If u dot is left child.
Is right child.
Okay, you want to do that?
Oh, no, you're right, you check.
You can do it either way.
It works,
Right.
I'm sorry.
If u dot is a left child, then u dot get parent dot set left child to u dot get right child. Else u dot get parent dot set. I'm a right child, so right child to u dot get right. There. And then set the parent regardless. Too many parentheses. There we go. Way more complicated. But let's test it out. 24 and 49. Okay. Come back over here, switch. There we go. Switch, compile. Hey, cool, it worked. Right. You could go through and do several more of these. I'm 60% convinced that that works. And we've got maybe 12, 15 minutes left here. Let's try to get that other one, right? Where if it has two children. Now, should this be the first thing that the last thing I check? I have no children. I have one left child, but no right child but no left child. I could come back over here and say, is only child, u dot is only child. Is there another term for that? And they are
No.
no, what?
Nothing.
Huh? Okay.
Yeah, I don't know what you're talking about.
Okay. Lucky? Not lucky. Siblingless? I don't know.
Said orphan.
Sid orphan. Okay. I'm going to actually promote this up to the top in the first thing that I check, right? If it has both children. If u dot has left child and u dot has right child, right child, then I've got that case. Otherwise, else, if. Right? It has two children. We now need to find the maximum value in the left subtree, replace that value with the current node, and then delete the max. Okay? So let's go ahead. We're not probably not going to get this done, or at least not fully tested. So let's at least try to get the maximum, right, in the left subtree. Okay? Now, oh wait, what if there is no left subtree? Let's come over here. All right. So here's the thing that I want to delete. What if there is no left subtree at all? Does it have both a left child and a right child then? Nope. So we're good. It definitely has a left subtree, right? So I will set, say, binary tree node max to be equal to u dot get left child, right? And then I'm going to go all the way to the right to get the maximum. So while max dot has right child, I will go to the right, go to the right, go to the right, go to the right. So max is equal to max dot get right child. Right. There we go. And let's print it out just to, in fact, let's not print it out. Let's go ahead and set a debug, or there we go. And let's come over here and set us up for something that we can test here. Say 50. There we go. And take this out here. There we go. yes, switch over to that perspective. All right. Oh no, it's gone out of scope already. So I can't set a breakpoint there because I don't have anything else. System.out.println max. I normally wouldn't do that, but println. But I need an line of executable code here so that the debugger would actually stop there. Right? And I'm about to print the maximum here, which is and predict what is it going to be. Let's go over here. Right. I'll get rid of all this. Right. Okay. I'm trying to delete 50. So what's the max? We already identified as 49. Okay. So is it? Hey, 49 works. Okay. I'm convinced that that all works so far. So let's get rid of this and go back to my Java perspective. Replace the value in the node with the max value. So u.set element to max.get element. There. Except that, oh, we don't have a setter. That's probably because I made it final. I now have a very good reason to change this. Make it not final, and where's the actual element? Now I can do my setter. Void set element to t element. This dot element is equal to element. Right. Okay. Before I didn't have a very good reason, but now I do. Right. I want to change it. Right. Keep things as conservative or as closed as possible until you have a reason to open them up a little bit more. Okay. All right. Now I still need to delete that maximum. Right. So it'd be really nice if somebody else did that for me. Delete node max. Right. What if I had a function that did that for me? Well, I've already got it, right? I've got the node right there, max.
Could you like recursively call delete?
I could, or I could redesign the function. Private void delete node. Right. And tree node, binary tree node. T, and I'll just say U. Right? Hey, that sounds familiar. That's what this is doing. Right? So what if we took all of this stuff, moved it up here and modified it? What would delete now look like? And we're not going to do it. I'll go ahead and move it all up here. And that's going to be a Boolean as well. And don't forget to do redesign this function, or this method, because I need to make sure that it, that I do change it. Right? Let's come back up here. So I'll still get the node. Well, I've already got the node. This is delete node. Where's my other delete? This is the one I want to change. Here we go. All right. So I need to find that node still. So, oops, darn it. I'm just going to steal this code again. All right. So I will find the node containing X. If it's equal to null, then I'll return false that I ended up not doing anything. Otherwise, I will go ahead and delete node of U. Right, there we go, and return true. So much cleaner, right? If I had something to delete nodes and get nodes, right, then deleting an element here is just done in terms of those things. Not only that, but now I can reuse it, right? I can go ahead and reuse this. I don't want to do it recursively, though, obviously. So that's why I've got my to-do here. All right? So I'm not going to find the node. Right? If it's a leaf node, then I don't know. Is this enough? I find the maximum, I set the maximum, and then I delete the maximum. Let's think about this recursively. If I come back up here, and I want to delete this node, right? Is it going to have both children? It was the maximum. Does the maximum have 2 children? It wouldn't be the maximum then. So yes, I can do this recursively. I want to make sure that it's not an infinite recursion or that I don't delete anything that I shouldn't, but is that going to happen? Is the max going to have both a left child and a right child? No, because it wouldn't be the max then. Huh. Okay. So, oh, and then we're always returning true here because I ended up deleting it. I don't need to do that then. I can go ahead and make this into a void function. And you're responsible for doing that. Let's see if it works. Cross my fingers here. Did we accomplish this in only 2 minutes? No infinite recursion. Right. Remember, it should be 50 that we're deleting. Right. Yeah, what should it, let's predict before we do that. What should it look like? I end up with 49 up here, and then 48 gets promoted up.
Yeah.
Right? Good. Switch PDF, recompile it. Oh, it was already compiled. Oh, no, it was not. All right, there we go. 49 is up there. 48 is up there.
Did we remove the delete 24?
Yeah,
Okay.
we did, and so it's still there. You know what? How can we really test this?
Stick it for, I don't know what.
Yeah, well, yeah, what? Let's come back over here and look at all, where's my tree? Stick it in a for loop and do what?
Delete everything?
Delete everything. Right? I'm gonna grab this and bring it over here. And for each one of these elements, I will say t dot delete that element. So I'm gonna delete all of these elements in some order, right? Delete X. There we go. Not only that, but I'm going to print it out every single time after the delete. Okay, it ran. Switch over to the editor here. And so we'll end up with, I don't know, a couple dozen. Come on, you can do it. There we go. All right.
Oh, that's funny.
There we go. So we end up deleting 50. Looks good. What's the next one we delete? 40, 60. We end up deleting 40. What should it be?
Highest, which is 48.
28. It's 28, right?
Oh,
Well, we go to,
based on the other child. Yeah.
yeah. So 28 goes up there, and it's gone. Cool. All right. Then we delete, what's next? 60? Yep, 60 is next, so that'll get deleted right there, and what happens? 90 comes up. Cool. What else did we delete? 20, 45. So 20 is right there. So what do? We go over here, get the max. 15 comes up here. 12 should come up there. Look good. Then I keep forgetting what. That was 20, right? All right. Next one would be 45 here, and that we got rid of that because 24 comes up. Next one that we delete is 90. So we get in the max. 85 comes up here, and it's a leaf. So great. Right. Next one we would delete is 10. Did we do that correctly? Yep. By promoting up 2. Dot, 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 dot. There.
Cool.
And then there is an empty picture sitting right next to it. It's just not rendered because it's 0 pixels. Looks like it works to me. I mean, and I automated it all. Right? I was really, really rigorously testing it by deleting all this stuff. Now, if you want to do it again, what you could do is you could go ahead and take all this stuff and throw it into a list, randomly permute it, jumble it up, shuffle it, delete everything in that order again, look at it, right? Delete do another permutation, delete everything in that order again, and take a look at it. But otherwise, I'm already at like 95% convinced that this works. Can you ever be at 100% convinced that it works?
Not without hiring one of those mathematical checker guys.
Exactly, the formal verification analysis. And even then, you have a proof that it's correct. How do you know the proof is correct? You prove it, another proof, and then it's a never-ending cycle, right? So, have you ever heard of Gödel's incompleteness theorem? That a system, a sufficiently complex enough system is not able to prove its own consistency. And it's just a mathematical, clever way of saying this sentence is a lie. Is it? It depends. If it's a lie, it's true. If it's true, then it's a lie and therefore it's false, right? If it's false, then it's a lie and therefore it's true, right? It's self-referential. So unfortunately, you're not going to take discrete math?
I may.
Oh, okay. Well, then let's end on one thing that I do in discrete math to show you this liar's paradox. Let me go ahead and create a set. S is equal to new hash set. Right. Note here that I am not putting in the parameterizations. Let me go ahead and import this and import this. All right. So S dot add 10, 20, 30, and let's print it out. System.out.system.out.println S. So what should that set contain? 20, 10, 30. Yeah, it's unordered, etc. All right. This is called Russell's paradox. S.add S. A set that contains itself. Right? So Russell's paradox was a realization that, wait a second, we can't just go willy-nilly and say a set can contain whatever you want. We have to have rules. We have to have axioms to start with. And so this is Zermelo-Fraenkel set theory, the set theory that you're introduced to. We never say that it's Zermelo-Fraenkel set theory with the axiom of choice, but that's what it is. Why? Because then you end up with things like this. This is Java's solution to the Russell's paradox. It checks, am I contained in myself? If so, I print out this collection as a hard-coded string.
So when you do this in C,
Yeah, how would you do it then? If you did this in C,
you went
what would you have? I contain myself. All right, well, what else do I contain? I contain myself. I contain myself. I contain myself. An infinite recursion.
stack smashing.
Bingo. So you can ask things like system.out.println s.contains 10. That should be true, right? Yeah. Now ask the question, do you contain yourself? It should be
Yes.
yes, it should be true. There's your stack smashing event. Stack Overflow. So they solved Russell's paradox by making sure that you didn't have this infinite recursion, at least as far as the toString method is concerned. But did they think to solve it for all the methods?
Nope.
Nope. And this is Russell's paradox, because Russell's paradox is, what if I constructed a set that contains sets that contain themselves? Now, does that set contain itself? It's a liar's paradox, right? And it's simultaneously true and false because it goes back and forth. False implies true, true implies false, and back and forth because it's self-referential. So Russell said, we shouldn't be able to do this. Right? Now, what's the real solution here with Java? The real solution to Russell's paradox is we shouldn't be able to do this. Set of integers, right? T is equal to new hash set of integers. Right? T dot add 10, 20, 30. Right? T dot add T. Nope. Russell says you can't do that. You need an axiomatic set theory in order to have rules, and you cannot violate those rules. There's your rule.
If
You can only hold integers, period.
if you don't give set a type like you did integer the second time,
That's
it'll just hold whatever. You can do
that's a
strings,
raw type.
integers, and
I could say s dot add hello.
got it.
In other words,
then you're living in, well, unresolved, no,
Oh, it's still up.
yeah, thank you, Java. All right, and go all the way back up here. There we go. Hello. Now, be careful because this is, I mean, you're living in 1999 Java right here, right, where you didn't have parameterizations. This goes all, and this is why I was comfortable covering this, because it is relevant to and germane to object-oriented programming, right? Without polymorphism in 1999 Java, you have Russell's paradox, right? You have these raw types, and you have really unsafe operations. You still have this in other languages. Take Python. Python, you can do whatever you want, and there are no ways to enforce those rules. Right? There's no way to establish those rules. Right? How does Python, you do Python in any courses so far?
We don't have to.
No, okay. How does Python solve Russell's paradox? No idea. It probably doesn't. It probably is a Stack Overflow. Try it sometime. How do languages solve these fundamental mathematical problems, right, that you never even thought about? Because no, we're not going to tell you about Russell's paradox. We're not going to tell you about Zermelo-Fraenkel set theory. We're just going to give it to you and say these are the rules. Right? Why are these the rules? Well, here's a 500-page book on Principia Mathematica of why things are the way they are, Russell and Whitehead. Right? And it has impacts on basic programming stuff that you would do in a first computer science course. All right, so enough of that. Have a good weekend. Oh, there's a, okay, oh, sorry, no, not a good weekend. I'll see you on Thursday. There's like a trophy emoji in the YouTube comments. I don't know what that means. Like, yay, I guess. All right, thanks for watching.